Hello and welcome to this video for Chemistry 30. This is the final video of the equilibrium acid-base units, and we're going to review titrations and pH curves as well as indicators, and we're also going to talk about buffer solutions. So first of all, the most common thing we use titrations for in Chem 30 in the acid-base unit is to determine the pH of the endpoint. Now obviously you can do other stoichiometric calculations such as calculating the concentration and volume at the endpoint, but the pH is really what we're going to be focusing on with pH curves. So a pH curve is a graph that shows what happens to the pH of the sample as you're adding either an acid or base to it. So the y-axis shows you the pH and the x-axis is showing you the volume of titrants being added to the sample. The endpoint is defined as where the reaction has gone to completion. So the moles of the acid equals the moles of the base. Now this is indicated by a color change, and there's indicator solutions that we're going to review today that we use to let us know when we've reached the endpoint. Equivalence point is the volume required to reach the endpoint. Now, when you're looking at a pH curve, there's initially a flat region that we call the buffer region, and there can be more than one buffer region if there's more than one endpoint. The initial pH of the curve must be the pH of the sample. The coordinates of the equivalence points, pH and volume must be accurate. The overtitration is always asymptotic with the pH of the titrant, and the number of equivalence points and buffer regions, like I said, must match the number of quantitative reactions occurring. So if you have a triprotic acid, it could technically have 3 endpoints. It could have 3, actually, sorry, it could have 3 buffer regions when we look at a graph. Now, the problem with triprotic acids is they usually don't quantitatively lose all hydrogens because they become very weak. So you might only see 2 endpoints, 2 buffer regions, for example. Okay? Let's look at some pH curves. Now, you could also be asked which titrants are you going to use. So if your sample is an acid, use a strong monoprotic base such as sodium hydroxide or potassium hydroxide. And if your sample is a base, then use the strong monoprotic acid, HCl. So the pH curves that you need to be able to interpret, first of all, we learned about strong monoprotic for acid and base titrations in Chem 20. So this is a review. A strong acid being titrated with a strong base means you're starting low and the pH is increasing. Okay? It makes this kind of S shape. The end point is the middle of that hill, which would be at 7 for a strong acid with a strong base. So your strong acid, again, could be HCl, and your strong base could be NaOH. Okay? If your strong base is being titrated with a strong acid, that means it's a base acid being added to it. It starts high, and then it goes low. But again, your endpoint pH is at 7. Okay, if I were to read off of with numbers, I could find the equivalence point volume required to reach these endpoints. If you're asked to do that, that's how you would do that. So the middle of the hill is the endpoint. Now, what if you have weak? If you have a weak acid, think of it as like if I have a weak acid, remember my titrant is always a strong base. So the strong base kind of takes over and makes the pH go higher. So it's a little bit higher than 7, maybe 8 or 9 at the equivalence point. And if you have a weak base with a strong acid, again, your titrant will always be a strong acid or strong base. Then the strong acid kind of overtakes and the pH actually gets a little lower. Now, it's a little more complicated as to why the pHs are not at 7. It has to do with when you have a weak acid and a weak base, their conjugate is fairly strong. Not strong, but strong enough to actually impact the pH at the endpoint. Okay. Also, that initial flat region, actually, I'm going to go back for a sec, just to label that this is your buffer region, this initial flat region. This is your overtitration region. Okay. So the initial flat is the buffer. The final flat is the overtitration, so meaning you've added too much. All right. Now, in these curves, the initial flat region is not as flat. So here's my buffer region, which is a little more steep, okay? My endpoint, again, being the middle of that hill, is above 7. It's maybe at 8 or 9, okay? And then if you have a weak base being titrated with a strong acid, these are still monoprotic, by the way. This is your initial buffer region. And then again, your endpoint, the middle of that hill, is a little bit lower down, maybe at 4 or 5, for example, or 5 or 6, okay? Usually you'll have numbers on your graph so you can easily measure what the pH is. Now, the third set of graphs that you can have are polyprotic. Your sample will always be monoprotic strong. Sorry, your titrant will always be monoprotic strong, but your sample can be polyprotic. If it's polyprotic, like I said, it's going to have more than one buffer region and more than one endpoint. This is probably a diprotic acid that is being titrated with a strong base. This is your buffer region 1. This is your buffer region 2, and those are your 2 endpoints. So for example, if this is H2CO3, it loses its first H to become HCO3, and then its second H to become CO3 2-. Okay? This is not a buffer region again. This is the overtitration. All right? Now, if you have a polyprotic base being titrated with a strong acid, same idea, multiple endpoints. Here's endpoint 1, here's endpoint 2. Now, this could be, for example, my CO3. It gains its first hydrogen here to become HCO3, and its second hydrogen here to become H2CO3. Okay? This is my buffer region 1. This is my buffer region 2, and this is my overtitration. So you could have questions asking you, how many buffer regions are there? How many endpoints are there? What is the endpoint pH? What is the equivalence point volume? Identify the acid and base that are reacting. Okay? So again, if there's multiple endpoints, you need to pick a polyprotic weak acid or a polyprotic weak base if it's starting high and going low. Here's a sample question. Which of the following graph represents the titration of a weak polyprotic base with a strong monoprotic acid? So it's starting high and going low. If it's polyprotic, it needs multiple endpoints, so that would be C. Now, indicators. How do we deal with indicators? An indicator is actually an acid base itself, and it has a different color whether it has its hydrogen on it. Okay? So for example, litmus paper, when it has its hydrogen, it's a red color. When it loses its hydrogen to become a conjugate base, it has a blue color. So they're actually acids themselves, weak acids in their conjugate base form that have a different color. So here's the chart that you guys have in your data booklet for Chem 30. There's abbreviations. So let's say you have methyl orange. So methyl orange, when it has its hydrogen below or at 3.2 is a red color. It loses its hydrogen to become the methyl orange ion above or equal to 4.0, and then it's a yellow color. Okay? So indicators have colors. They have Ka values too because you could even use them in pH calculations. All right? Now, how do we use them in a titration? You want to pick wherever your endpoint pH is, you want to pick the indicator that's going to change color right after you reach, or right when, ideally, you reach that endpoint. Okay? So if you're starting low and going high, let's say the endpoint is 3.5. I'm going to pick methyl orange because it's going to change going low to high shortly after 3.2. Okay? So check again what your endpoint pH is and pick which indicator would most likely change right after the sample fully reacts. Now the last thing we have to talk about are buffers. Now buffers are essentially something that prevents a large pH change. It does so because it is a large amount of a weak acid with the salt of its conjugate base. So for example, H2CO3 with the HCO3 -1 ion. Now, negative ions, again, are never going to be found by themselves. So sodium, for example, has been added to it to make a salt out of it. A salt is just an ionic compound. Okay, but specifically, this is my weak acid. This is its conjugate base. There's large quantities of them, so that if an acid or a base are added, small amounts, of course, they're going to prevent a large change in pH. They can be overcome, but they try to protect a large change in pH. Okay, so the acid will protect against any base added, and the base will protect against any acid added. Like I said, they can be overwhelmed if you add too much acid or base, meaning eventually the pH will change if you add too much acid or base. But here's a type of question you might see. I have an acetic acid sodium acetate buffer system. So what I have is acetic acid, CH3COOH, and it's acetate ion, which was bonded with sodium just to make a compound out of it. Okay, so this is my weak acid. This is also a weak base. It's the conjugate base of the acid. Now, what happens when a small amount of strong acid is added? Well, that strong acid excuse me, is going to ionize into hydronium ions, and it's going to react, because it's an acid, with the base portion of the buffer system. Okay, so essentially almost like predicting a reaction. You list what you have, you pick the strongest acid and the strongest base. The strongest base would be the weak base of the system. We transfer our hydrogen from the acid to the base, and now I produce water, which is the conjugate base of the acid, and I'm making acetic acid, which we already had large quantities of. So that's why this withstands a large change in pH, because I'm making products, water, which I already have, and acetic acid, which I already have. So it's going to prevent against that. So if I add an acid, the base portion, the acetate ion, is going to react with it. And then if I add, so this is just showing again, you could just list everything present, pick your strongest acid and your strongest base, and react them. If I add a small amount of sodium hydroxide to my system of acetic acid and its acetate ion, this time the acid portion, that's my weak acid, is going to, that's a weak base, sorry. My weak acid is going to neutralize the hydroxide that we've added. So again, my acetic acid will react with the hydroxide ions that are being added to neutralize them, because we are going to produce water, which is neutral, and the acetate ion, which again we also had a large quantity of. This is why, again, when you're picking a buffer, it has to be a weak acid so that the conjugate base of it is strong enough to actually neutralize any acid being added. Okay? So just like predicting a reaction, you're transferring the hydrogen from the acid to the base to make your new conjugate acids and bases. When a base is being added, the acid portion of the buffer system neutralizes it. If an acid is being added, the base portion neutralizes it. So you have a large quantity of this weak acid with its weak conjugate base, but they're fairly strong enough that they will neutralize when a small amount is added. That's the key there, a small amount is added. Okay? So let's say we have a sample diploma question. If each of the pairs listed above is mixed together in equal amounts, then the pair that would act as a buffer, well, first of all, this is not the conjugate base of that acid, so that can't be right. Here I do have conjugate bases of my acids, because remember, the salt means that there's just a group 1 ion usually bonded to it. So how do I identify which one is correct? Well, 2 is a strong acid and 3 is a strong acid. So it can't be those. It has to be a weak acid with its conjugate base. So the only weak acid in that list is H3PO4, and that is the H2PO4 ion bonded with sodium to make a salt out of it. So that is my weak acid with its conjugate weak base. So the answer is D. Okay? And that, my friends, is it for this lesson and this unit. Thank you very much for watching.